So last time, we've been talking about images and pre-images. Okay, so we defined the pre-image of a function, a, under f. So you have a function, there it is. We have a function, f from D to R, domain to range, and a is a subset of the range instead of the subset of the domain. The pre-image of A under F is written like this, and it's the set of all domain elements that go into A. So here's A, right? And then every arrow of that function F that goes into A is included in the pre-image of A. Please don't think of F as a function. It isn't. Well, it's not a function from the range to the domain. It's actually a function from the power set of the range to the power set of the domain. Okay, but I don't really want to cover it in that light. The notion of an inverse function again is a little bit well. It's not a little bit tricky. It's very limited. We'll get to it. So we did an example here, and then we proved the following. Let f be a function from domain to range, and a and b be subsets of the range. A subset of b implies pre-image of a is a subset of the pre-image of b. We proved that. And then we proved the converse statement, that the pre-image of A is a subset of the pre-image of B implies A is a subset of B, which was different than just image. Image doesn't quite behave as nicely. Pre-image behaves more nicely for some weird reason. So basically we have an implication and its converse are both true. And normally the way that is stated is as follows. Given f from domain to range and a and b subset of the range, a is a subset of b if and only if pre-image of a is a subset of the pre-image of b. And that proof, the proof of this, includes two proofs. A is subset of b implies pre-image a subset pre-image b, and pre-image A subset pre-image B implies A is a subset of B. Let's do a couple more examples like that, a little bit more analysis of this. So, proposition. So let's go back to image for a moment. So let f be a function from domain to range, and a and b be subsets of the domain, since we're going to talk about images. Okay. The image of A, not the pre-image, the image of A and the image of B are disjoint implies, remember disjoint means their intersection is empty, implies A and B are disjoint. Disjointness of the image implies the original sets were disjoint. Proof? So now we've talked about two ways of proving implication statements. We've talked about direct proofs, and in the previous homework on chapter 3, we did proof by contradiction, if you recall, right? So to prove P implies Q is true, okay, use one of the following. All right, there's direct proof. All right, assume P is true. Show that Q is true. And proof by contradiction, assume P and Q naught is true, find a contradiction. And there's also proof by contrapositive, which is a direct proof, sort of backwards. Proof by contrapositive. So that is, assume Q naught is true, show that P naught is true. So that is prove prove the contrapositive. Q naught implies P naught. So we've talked about three types of ways of proving. Well, there's three ways of proving anything, but here we're just talking about an implication. Now, this type of statement is somehow not really amenable to a direct proof. Okay, it needs a contradiction proof or a contrapositive proof. Because probably, when you're trying to say that, given nothing, you have nothing. There's nothing to work with, so to speak. There's nothing to work with, so to speak. So proof by contradiction is, given something here, you have something there. That does, or given nothing here and something here. When you have a something, you can do something with it. Sorry, that's just way too abstract, but that's sort of the idea, and we'll talk about that as we go along. What sorts of things are really naturally done by contradiction or contrapositive rather than a direct proof. But this one we're going to do. Let's do it by contradiction. Contradiction. Yeah, let's do it by contradiction. Okay, so we're trying to show that image of A and image of B are disjoint implies A and B are disjoint to start with. So what do we assume? Well, what's the first thing I write before I assume anything? There's a little clause you should write when you're doing a proof by contradiction. When doing a proof by contradiction, you should always start with these few words.
Helps you turn the mic on, actually. Let us assume the inverse.
The mic is off? No, my mic is on.
My mic was on. I wish to talk to you, my mic was off.
Sorry. Okay. What words do you start with?
Let's assume the inverse of the statement.
Assume the negation. Assume not.
Yes, negation.
So some say assume not. That's a little bit sort of. That's fine. It's correct. It's a little more nebulous than other things. I mean, by way of contradiction, leaves no doubt what you're talking about. way of contradiction, assume that what? What are we going to assume? So we're trying to show P implies Q. So we assume P and Q naught. Assume what? Come on, guys, wake up. We need that conversation. We need to think about what we're saying here. We're talking about an implication. P implies Q. Okay, here's the implication. P implies Q. So by way of contradiction, assume P and Q naught. So what am I assuming here in particular, in this particular instance? Assume that what?
I'm the only one allowed to talk. F of A and F of B equals nothing.
Yep.
And implies
the
the
negation of P implies
Q.
And
yeah.
Or you could say but.
Not A and B.
Right, not A and B is empty, meaning what? A and B is
something.
So not empty like that. Okay, so since A and B is non-empty, what can you do?
Assume X is the answer to, is an element of the answer of A and B.
Yeah. Let X be an element of A intersection B. By definition of image, we now have that what? So X is, well, so before that, let's say, whoops. So X is an element of A and X is an element of B. By definition now, what? F of X is an element of functions. They are a stumbling block.
Would that be F of X is an element of F of A and then of F of B?
Yeah, it's also an element of F of B. All right, so F of X is in where?
The union of F of A and F of B.
Intersection.
Or intersection, sorry.
Well, anything wrong with that?
Yeah, that's contrary to the previous.
It's contrary to that. A contradiction of the assumption FA intersection FB is empty. And that's it. Functions. They are a stumbling block. Okay, need to spend a little time with it. Any, I mean, you think about, I mean, if you have a hobby of some sort, or you like some kind of sport, watching a sport. I mean, baseball fans are kind of like this. Like, baseball fans are all about, statistics and rankings, and well, not all of them, but a lot of them are, interested in statistics of baseball, and who's the better batter and who's the better pitcher and why the statistics show that and all this sort of thing. And, sometimes you wonder, gosh, how do you remember all that stuff? Well, the answer is very simple. How do they remember all that stuff?
Spend hours doing it.
Yeah, they spend a lot of time doing it. I mean, or
My brother, big into video games, and he knows like all the numbers in certain games he plays, and I'm just like,
yeah,
so many options. How do you calculate this?
Right. I mean, like with video games too. I mean, because I mean, gosh, they're so complicated nowadays compared to when I was a kid. It just requires time. Time breeds familiarity, and that's really all there is to it. Y'all got this far in your mathematical education. There's nothing here that's beyond you, trust me. But it's a new way of thinking, so you got to stretch your brain a little bit on it. Okay, so fine. So, I mean, as you see, the proof is just 2-3 sentences here. All right, so the proof by contradiction is really the way to go there. All right, so image of A intersect image of B is empty implies, image A and image B disjoint implies A and B disjoint. What about the other way around? What about the converse? Does A and B equal to the empty set imply the image of A intersect image of B equal to the...
I have a question real fast.
Sure.
How do you identify, is the image of A and the image of B just regular functions, or how do you identify them between functions?
The image of A, sorry?
So you're saying the image of A, is that just a function? Because it's being written as a function.
It uses the same notation, but it's not a function from D to R in that sense.
Okay, so it's just one of those things that you just have to recognize that it's...
Right, so given a function f from D to R, right? Taking x in D, right? F of x is in the range, but also you can do f, I don't know, maybe like hat from, this image function from the power set of D to the power set of R, right? By f of D, or f of A is equal to the image of A. So you can sort of take a function and extend it to a function on power sets.
Okay, I was looking for the different notation.
Yeah, we don't use different notation. I mean, it makes sense, that notation, because it's an extension of what the function does. That's way standard in math. That you take a notation that's used for something, and then you generalize it to a different situation. I mean, and that goes in lots of different ways. I mean, not just with functions.
Oh yeah, I know. That's one of the things that drives me crazy sometimes.
Right, like
tangent on arcs and stuff with just the -1. I'm like, that's bothering me.
Yeah, I mean, like in algebra, in abstract algebra, what you'll find is like, I mean, if A and B are sets of numbers, then by A plus B you mean the set of all A plus B, such that A is in A and B is in B. right? So it's this set of all the possible sums between elements of A and elements of B. So, I mean, they just use that same notation, this addition notation, to describe this operation on sets suddenly, when your sets of numbers. So, just a standard thing. It goes like that. And that's, I mean, the notation suggests what it means, because it's an extension of its original meaning. Okay, so what about the converse? Does A and B disjoint imply f of A and f of B disjoint? Answer is certainly not. Can anyone give me an example? Counter example, I mean. Give me a counter example where A and B would be disjoint, but f of A and f of B are not disjoint. All right, given f of x equal to x squared, let's go just to functions of real numbers. All right, A equal to -1 and -2. Right, and B equal to the closed interval from 1 to 2 are disjoint. But the image of A, right, which is the set from 1 to 4, is equal to the image of B. So not only are they not disjoint, they're they're same. This is a crappy example, though.
Why is it a crappy example?
Crappy example.
Seems like
Sorry for the language. Strong language is needed in this instance. When something is that distasteful, you have to say so. Why is it a bad example? I mean, it's fine. It's a correct example. Correct isn't enough, though.
But you only need one piece of proof to disprove the statement. So I would think a quick and clear example would be
Exactly. The cheesier, the better. I mean, the more ridiculous the example that shows the statement is false, the more you have humiliated your foe, which of course is your goal. the more have you displayed the absurdity of the statement. Okay? So, I mean, a sophisticated example, sometimes, because when you give the cheesy example, then your your adversary will say, this is math humor. This is way beyond the scope of the course. But anyway, your adversary will say, okay, fine. So let's exclude your cheesy example by modifying the statement this way. And then you say, well, it's still wrong. Here's a more sophisticated example. So, yeah. Anyway, so the reason why I say this is because sometimes, like in jest, really, I mean, it's kind of like that among mathematicians. I was at a conference once. Sorry, I got to lapse into story time. I normally don't do this, but I have to do it because it's just so funny. And if you knew the people, it would be even funnier. So I was at a conference. It was maybe like 10 years ago, and this one guy who's very famous. He's a world famous mathematician. I mean, he was a professor at Princeton University, which is pretty much the premier institute of mathematics in the world. And he made a statement which was incorrect, or made a conjecture. I conjecture the following is true, and it was very much incorrect. And someone in the back of the audience, a friend, another guy about the same age. They're much older than me. They're probably in their almost 70 at this time. But the one guy said, "Well, Paul, that's not right. What about this?" And he said, "Okay." And I said, "Oh, really?" And anyway, so then the next day he got up and said something else, and the same guy said back to him, it was a different statement, but the same guy said back to him, "Oh, Paul, that's not really right. What about this?" As a counterexample to your statement. And Paul says, "Well, what's wrong with my proof, my pseudo proof?" And the other guy said, "Well, I really don't care. It's way off." He said back
Nice.
to him, "Well, you don't have to be so rude about it." And then the other guy said, "I think the score between us is 40-love, Paul." So it's all in good humor. So anyway, so here's a simpler example. Anyone want to give me a simpler example? Right, that A and B disjoint. A and B disjoint does not imply f of A and f of B are disjoint.
One, you only need two dots on the domain, 1 and 2, one
There you
dot
go.
on range.
Mhm.
Both go to it.
Just like that. Right? Okay. So this is a better example. It just, it just is, it's not. I mean, it looks like, at first glance, oh, yeah, maybe that's true, but, it looks good, but it's still not right. Interestingly enough, preimage behaves much better. So, given a function f from domain to range, and A and B, a subset of the range, A and B are disjoint if and only if the preimage of A and the preimage of B are disjoint. So here, A and B disjoint implies preimage of A and B are disjoint, and preimages of A and B are disjoint if implies A and B are disjoint. So there's two proofs necessary here. Two directions of the proof. So remember when we were showing that, like, if x is equal to y as sets, we had to show that x contained in y, right, and y was contained in x. We had to show both of those, right? This is just like that, right? Implication is a containment relationship. Implication is a containment relationship. So we have to show that this implies this. And then we have to show that this implies that. Let us do them by contrapositive both. Let us do them both by contrapositive. But first you have to say what you're doing. I mean, you really got to be clear about where you're going, okay, and what you're up to. So first we're going to show that A implies B equal to the empty set. A and B disjoint implies preimage of A intersect preimage of B is empty as well. So first we're going to prove the statement in this direction. Now normally you don't write it like this. Normally you'll just write the following, because sometimes it's just too much to write that. You just write an arrow. Okay, so two parts of the proof. This first part is going to be A intersect B empty implies preimage A and preimage B intersect in the empty set. Okay, so to show that A intersect B disjoint implies F intersect A, F intersect B are disjoint. Oops. To show that A and B are disjoint implies preimage of A and preimage of B are disjoint. Let us assume use the contrapositive and assume that the preimage of A intersect the preimage of B is not equal to the empty set. Preimage of A and the preimage of B do not intersect, do not have empty intersection. What does that mean? What does that mean? That preimage of A intersect preimage of B, their intersection is non-empty.
It would mean that there's something that they share in common.
Yeah, so let X be an element of the preimage of A intersect the preimage of B. By definition, what? Well, thus, right? X is in the preimage of A, and X is in the preimage of B. So if X is in the preimage of A, if X is in the preimage of A, what's in A? Right? Think of that picture. Think of that picture for preimage. Let me copy it over as a matter of fact. Sometimes a picture says 1,000 words. Sometimes the picture is the proof. In this case, not really, but it can help. Right, so if X is here, if X is right there, what's this right here? If this dot here is f of x, right? If x is in the preimage of A, by definition, when you hit it with f, it goes into A. The preimage of A is all the stuff in the domain that goes via f into A. So by definition, f of x is in A, and f of x is also where? Because it's in the preimage of B.
F of x is in B.
Is in B as well. Therefore, f of x is an element of A intersect B. So A intersect B is non-empty. Is that the statement that we wanted? We're using contrapositive. So we're trying to show A intersect B empty implies preimage A intersect preimage B is empty. For contrapositive, you assume this is not empty and prove that this is not empty. Right? To show A intersect B empty implies preimage A intersect preimage B is empty. Lets us use the contrapositive and assume preimage A intersect preimage B is not empty, and conclude that A intersect B is not empty. So that's exactly what we wanted. When you get what you wanted at the end there, sometimes it's nice to say something like as required, as required, or which is what we wanted, or blah, blah, something like that. Okay. So now let's do the other direction.
I have a question real quick
Sure.
about this.
Mm-hmm.
Couldn't you use basically the same proof for that to solve for the other implication, except instead of doing a contrapositive, doing it by contradiction? Wouldn't that proof look pretty much exactly the same?
Yeah, contrapositive and contradiction can often be very, very much similar, very close. Like sometimes, like to prove P implies Q by contradiction, you'll assume P and Q not, and then you argue, and you come down to Q and Q not. In that case, you could have done it by contrapositive usually, rather than contradiction. When you
Okay.
your assumption itself, then probably it's okay. I mean, either or is fine. It's not incorrect.
Yeah. I mean, it just looks very similar. Like
Mm-hmm.
as far
Sure.
as the second implication, you
Sure.
can
Yeah.
prove it in a very, very similar way
Sure.
to what you just did.
Yeah. I myself, I normally don't use contrapositive much. I usually use contradiction or direct. So now we need to do the other direction, and that is to prove that. What is this? Save it before it crashes. All right, now. All right, to show that. So now we're doing the implication in this direction, from right to left. So to show that, so we wrote the statement like this. This is P and this is Q. P if and only if Q. So you have to show P implies Q, and then the other thing you got to show is that Q implies P. Right? Or you can write it the other way around. Q implies P. Right? So that's what that arrow symbolizes. So to show that the preimages of A and B are disjoint implies A and B are disjoint. Let us again use the contrapositive and assume that A intersection B is non-empty. And then we'll argue to preimage A intersect preimage B is non-empty. Not much argument is necessary. It's pretty much immediate. All right. So because A and B are not disjoint, what do we have?
X is an element of A and X is an element of B.
Yeah, so let X be an element of A intersect B. That is, X is in A and X is in B. All right. So what? Ooh, actually, it's actually not true what I said. Hold on. Yeah, this is actually not quite true. I apologize, I thought it was. Given a function, I have to add one more assumption. Given a function from domain to range, and a and b a subset of the range, assume that the image of f is the entire range. There's nothing in the range that you miss, in other words. There's nothing in the range that the function misses. If there's something in the range that the function misses, then this isn't true, because, like, you can have this kind of thing, like, you know, the function sends everything over here and over here, but then there's this thing x over here, and that's, you know, in a and b, but it doesn't come from anything over there, so there's a problem. Okay, so now because the image of f is all of the range, and, you know, x is in the range, there is what should we call it? I want to say y. There is w in the domain such that w, f of w is x. Let x be an element of A intersection B. So x is in A and x is in B. And because the image of f is the entire range, right, so let's include a picture. So here is x in the range. Therefore, there's something in the domain that goes to that guy in the range. The image of f is the entire range. The image of f is f of the domain. Right? There's some domain element that goes to that range element, which does not have to happen. Okay, with functions. It could be that a function doesn't, right? I mean, like f of x equal to x squared. Right? The domain is the set of real numbers, and the range is the set of real numbers. Right? But the negative numbers in the range don't get hit by anything from the domain. So we need just that little assumption. So let x be an element of A intersection B, and then that x in the range must come from some element w in the domain. So by definition, w is an element of what? W is an element of what? Because f of w is x and x is in A, w has to be where? I mean, like, here's A, which has got x in it, and here is preimage A, which has got w in it. Right? W has to be in the preimage of A. And because x is in B and f of w is x, what else has to be true?
Same thing with B.
Same thing. W is an element of the preimage of B. So f inverse A intersect f or preimage A intersect preimage B is not empty, as required. So that's the end of the proof there. So next time, think about the following. Next time, come up with a counterexample to the statement A intersection B equal to, not equal to the empty set, implies preimage of A intersect preimage of B is not equal to the empty set. Maybe we should do it the other way around. No, that's fine. Come up with a counterexample to this statement. A intersection B disjoint, or A and B disjoint implies preimage A, or sorry, A and B not disjoint implies preimage A and preimage B are not disjoint. Come up with a counterexample, and you're going to have to assume that there's something in the range which isn't in the image of the function, and you're going to have to use that element. Essentially, that element is going to be the intersection of A and B. Use domain equal to, keep it real simple. 1, 2, 3, 4, 5. And range equal to, let me use domain. Use this diagram. I like this better. 1, 2, 3, 4, 5, and range equal to, just say A, B, C. That's all you need. Okay, come up with a counterexample. So essentially, like, or maybe I shouldn't use A, B, C. Let's say X, Y, Z. So basically, your set A is going to be Y and Z, and your set B is going to be X and Z. So they intersect in Z, but Z won't be in the. So this picture does it. Z will not be in the image of the function. Okay? All right. So we'll go over that example next time, but try to come up with one on your own, okay? All right. New concept with functions. So a function f from domain to range is called, and there's two terms for this. One-to-one, or injective, when for every A and B in the domain, FA equals FB implies A is equal to B. I should write implies. So in other words, okay, no element in the range has more than one arrow of f coming into it. So, for example, so this domain range right, this is not injective because this guy has two arrows coming into it. Not injective, or not one-to-one. This one is injective. Every element of the range has at most one arrow coming into it. What about real numbered functions? F of x equal to, so f from the reals to the reals given by fx equal to what is not injective.
F of x equals x squared.
Sure, x squared. Right, that's not injective because 115. Okay, so next time we'll go over that example and come back to the notion of injections. Okay. All right, guys. Have a good afternoon. We'll see you on Friday.
See you Friday.